Greetings everyone, especially to our professor, Mr. John Patrico Galesco. We are excited to share our work with you. Let me start by introducing myself and my group mates. My name is Shane Marian Datulia.
I'm Devera. I'm Asuncion.
I'm Ricky May Bachansila and we are two CSA.
The Campus SCERMS class serves as the central entry point of the Smart Campus Emergency Response Management System. When the program begins, it initializes all core components needed for emergency management, including a map of responders, a binary search tree to store emergencies, and a graph structure representing the layout of the campus. Alongside this, the system also sets up the dispatcher, which handles routing and response assignment, and the summary report module, which logs all emergencies activities and statistics. To establish the virtual campus, the main class creates several locations such as Uptown, Central HQ, Industrial Zone, Downtown, Airport Hub, Riverside, and Residential Zone, and connects them using weighted edges that represents travel distances between these areas. This graph acts as the foundation for the dispatcher's path finding mechanism, allowing it to determine the shortest route for emergency units. The program also loads initial dummy data, which includes several responders of different types, example, police, fire, and medical, along with their starting location. Additionally, a set of sample emergencies is inserted into the BST, each one prioritized by urgency so that the system can efficiently retrieve and process the most critical incidents. Once initialization is complete, the program enters a continuous menu-driven loop where user can interact with the system. Through this interface, a user can add new emergencies, register new responders, view all current emergencies in order, inspect responder information, dispatch a unit to a selected incident, print the entire map graph, generate summary reports, or run a fully automated continuous simulation. When an emergency is added, it is stored in the BST and logged as pending. This patching involves selecting a specific emergency by ID, retrieving it from the tree, and having the dispatcher determine the closest appropriate responder using the graph. The result of each dispatch attempt is recorded in the summary report, marking emergencies as resolved or leaving them pending if no unit are available. The summary report feature generates an analysis of system activity, which includes total distances traveled by responders, a detailed activity log, and a display to the highest priority unresolved emergencies. The continuous simulation option builds on this by automatically selecting the highest urgency unresolved emergency, attempting to dispatch a responder to it, logging the result, and then moving on to the next one. This cycle continues until emergency are resolved or until the system encounters a case where no responders are available, at which point the simulation stops to prevent an endless loop. We created a class called Activity that stores all the important details about an emergency in our system. We included information such as the emergency ID, type, location, urgency level, the responder assigned, the travel distance, and the status of the emergency, whether it is resolved or still pending. All of these variables are private so that the data stays protected. We also added a constructor that initializes all of these fields whenever we create a new activity object. To safely access the data, we provided getter methods for each variable, allowing other parts of the program to read the values without directly modifying them.
Let's discuss about BST. In BST, there is node class. Inside the BST, each element is stored in a node holding the emergency data or the actual object, left pointer to the left child, right pointer to the right child. Next is the insert. Insert emergency adds a new emergency into the BST. How insertions works. If the tree is empty, the new emergency becomes the root. If the new ID is smaller, go left. If the new ID is greater, go right. If the ID already exists, replace the data with the new one. Next one is search. Search int ID looks for an emergency by its ID. How it searches. If the current node is null, not found. If the ID match, found. If the ID is smaller, search. If the ID is bigger, search. This uses the BST's ordered structure to find things fast. Next one is delete. Delete int ID. Removes a node by ID. Deleting a node has three cases. Case 1, leave or no children, just remove it. Case 2, one child, replace node with its single child. Case 3, we have two children, and find the smallest nodes in the right. Sub 3, this keeps the BST valid. Copy its data into the current node, then delete the smallest node. In order printing. Print order prints the BST in sorted order based on ID. The pattern, left, current, right, that naturally prints from smallest ID to large ID. Number 6, converts tree to array. To array, open and close parentheses, returns emergency. Counts how many nodes exist. Create an array of that size. Fill the array using in-order traversal. Overall summary, this BST class stores emergency objects ordered by ID, can insert, search, and delete efficiently, can print data in sorted order, can export the whole tree as a sorted array. It uses classic BST logic, or smaller is left and bigger is right. Now I'm going to discuss dispatcher. Dispatcher, it is a responsible for selecting the best available emergency responder and assigning them to handle an emergency. It uses two inputs. One is graph, representing location and distances between them. Number 2 is map, string responder, or a collection of all responders. How dispatching works. Number 1, gather all responders using responder all is equals to responder that get all value. Number 2, identify which type of responder is needed. Code is to responder type, emergency get, that get type is emergency description like fire in building, etc. is converted into one of fire, medical, or police. Number 3 is iterate through all responders and filter out invalid ones. The dispatchers ignore them if they are null, not available, type does not match, and cannot reach the location. Number 4, for each valid responder, compute the shortest route. String bracket path is equals to grab that shortest path. Get current location, emergency get location. If no path is equals to invalid or unusable. 5, choose the best responder. The dispatcher keeps track of the responder with the shortest travel distance. Here is the code. If this less than this, best this is equals to this, best is equals to R, and best path is equals to path. If no responder qualifies, the dispatcher return new dispatch result, false, nulls, -1, and null. Number 6, if a responder is found, print dispatch details. The program prints responder ID and type, destination, distance, and route. Number 7, set responder status to busy and move them. Here is the code. Best.set available, false. The responder is now marked busy and is considered located at the emergency site. Number 8. Simulate emergency completion. Simulate finish. Best. Number 9. Mark the emergency as resolved. Here is the code emergency.mark resolved. In summary, the dispatcher finds all available responders at the correct type, compute shortest travel and paths. Select the closest responder and assign them to the emergency, simulates completion, and return a summary result. For the last of my part, I will going to discuss dispatcher result. Dispatcher result is a simple data container. It used to store the outcome of some dispatch operation, likely in a system that sends a responder, like an ambulance, police, or medical, to a location. Public final Boolean success. It indicates whether dispatch succeeded. Next is public final string responder ID. The ID of the responder that was dispatched. Public final distance. The distance traveled or the distance from the responder to the target. Public final string path. The path taken represent array of strings. In summary, this class is an immutable result object describing whether dispatching succeeded, who was dispatched, how far they traveled, and lastly, the route they took. That's all.
Dangay greetings, I'm Rika May Batyansila and I will explain the emergency class, draft class, and map class. It starts in emergency class. The emergency class represents a single emergency incident and stores all important information related to it. Every emergency is automatically assigned a unique ID using a static counter that increases each time a new object is created. The class contains fields for the type of emergency, the location where it occurred, a description of the situation, an urgency level from 1 to 10, and a Boolean value indicating whether the emergency has been resolved. The contractor initializes these values, ensures that the urgency stays within the valid range, and assign a new ID to the emergency. The class provides several getter methods, so other parts of the system can access emergency's details, as well as mark resolve method that change the status to resolve when the incident has been handled. The toString method returns a formatted string that neatly displays the emergency's ID, type, location, urgency level, and resolution status, making it easy to print or view the emergency in logs or lists. This Java program implements a graph using custom linked structures to represent location and the roads connecting them. The edge class represents a single road from one vertex to another and stores the destination name, the distance, and the pointer to the next edge. The vertex class represents a location in the graph. Each vertex has a name, a pointer to the first edge in its adjacent list, and a pointer to the next vertex. All vertices are linked together starting from the variable head, forming the entire graph. The addVertex method inserts a new vertex at the start of the vertex list, checking first with getVertex to ensure it does not already exist. The edge method connects two existing vertices with a weighted road. It creates two edge objects, one in each direction, making the graph undirected. Each edge is added to the front of the vertex edge list. To compute the shortest path, the code uses Dijkstra's algorithm. It first collects all the vertex names into an array for easy indexing, then creates three arrays: dist to store the shortest known distance to each vertex, visited to track which vertices have already been processed, and previous to remember the vertex that comes from before each one in the shortest path. All this sun starts in infinite, and starts vertex is to set 0. The algorithm repeatedly selects an unvisited vertex with the smallest distance using getMineIndex, then checks all its connected edges. If going through that vertex gives a shorter route to a neighbor, the distance and previous pointer for that neighbor are updated. After all reaches and vertices are processed, the build path method reconstructs the final route by following previous chain backward from the end to the start. The path is reversed and returned as a string, where the first element contains the total distance and the remaining elements list and the vertices in order from start to the end. Finally, the print graph method prints a readable version of the graph by showing each vertex and all its connected edges, including the destination and the weight. Overall, the code builds a complete graph structure, supports adding vertices and weighted connection, including a full implementation of Dijkstra's shortest path method for finding the most efficient route between two locations. The map with key type and value type V class is a custom implementation of a hash map that stores key value pairs using an array of linked lists to handle hash collisions. Each key value pair is presented by an inner entry object, which contains a key, its associated value, and a pointer to the next entry in the same bucket. The map maintains an array called table, with a fixed capacity of 31 buckets, and each bucket can store multiple entries that share the same hash index. The hash method converts a key into an array index by applying the key's hash code and taking the remainder modulo the capacity. When inserting a new pair with put, the method first checks whether the key already exists in the bucket. If it does, the value is updated, and if it not, a new entry is added to the front of the linked list. The get method searches the bucket for a specific key and return its value, or null if the key is not found. The remove method deletes a key value pair by adjusting the linked list pointers and decreasing the size. The class also provides contains key to check for the existence of key. Size return the total number of stored entries and get all values to collect all values into an array by iterating through every bucket. Overall, this implementation demonstrates how hash maps work internally using hashing, buckets, and linked lists to efficiently store and retrieve key value pairs.
This is the responder class, which represents each emergency unit in our SCERMS system. I start by declaring the class as public so it can be accessed by other parts on the program. The first field is the private string called ID, which stores the unique identifier of the responder such as A01 or PO2. Next, I have a private variable name type, which uses the custom enum responder type to identify if the responder is police, fire, or medical. The current location variable stores the location in the city where the responder is currently assigned. The available variable is a boolean that indicates whether the responder is free or currently handling an emergency, and it is set to true by default. This is the constructor, which initialized a new responder object using the given ID, the type of responder, and the starting location. I assign by the past ID value to the class's own ID variable. Then I assign the given responder type on the type variable. And finally, I set the responder current location based on the value provided when the object is created. The getID method returns the responder's ID. The getType method returns the type of responders such as medical, fire, or police. The getCurrentLocation method returns the responder's current location. The isAvailable method returns true if the responder is free and false if they are busy. The setAvailable method allows other classes such as the dispatcher to change whether the responder is available or not. The setCurrentLocation method updates the responder's location after they have been dispatched. The day-label method converts the responder's enum type into a more readable label. Then, inside this method, I use a switch expression to check what type of responder this object represents. If the type is medical, the method returns the word ambulance. If the type is fire, it returns fire truck. If it's not medical or fire, the default label returned is police unit. Next is the table row method creates a formatted string used to display responders in the table format. I use string.format to align each columns neatly by specifying fixed spacing or the fields. Here I insert the responder's ID, the readable type label, and the current location, and either the word available or busy depending on the responder's status. This line begins building the output by adding the ID, the responder's type, and the current location. And this part insert the responder's availability and closes the braces to complete the string. Public enum responder type. This line defines an enum called responder type. An enum is a special type in Java that let us create a fixed set of constant values. Police, fire, and medical, these are the three constant values inside the enum. They represent the different types of responders, the police, fire, and medical. These values are predefined and cannot be changed. In line 3, I start the class definition for summary report which handles all reporting and summary outputs in the system. In lines 5 to 7, these three lines declare the main data structure, a map of responders, a binary search tree for emergencies, and a graph for location. The lines 9 to 10, these track how many dispatches occurred and the total of distance traveled by the responders. Line 12 to 13, I create an array to store activities logs with an initial size of 32 and a counter to track how many activities I've added. In lines 15 to 18, this constructor accepts the responder's map, the emergency BST, and the graph. I assign each of them to the class fields for later use. In the line 27, if the distance passed in a 0 or negative, I ignore it. In line 28, I increase the total number of dispatchers. In line 29, I added the distance to the running total. In line 33 to 36, here I check if the activity array is full. If it's not, if it is, I double its size by creating a temporary array and copying the old values into it. In line 37, I store the new activity into the array. In line 38, I increase the activity counter. In line 44 to 47, I print header lines to format the responder table. In line 49, I get all responders using get all values. In line 50 to 52, I loop through all responders and print each row using the responder's own table row method. In line 57 to 60, I print the header for the activities table using formatted print output for neat alignment. In line 63 to 73, I loop through each recorded activity and print its details, the type, location, urgency, responders assigned, distance, and the status. Line 78 to 79, I get all emergencies from the BST and count how many there are. In line 81 to 83, I count how many emergencies are resolved. In line 85, I calculate how many are still pending. In line 87 to 89, I compute the average distance traveled. If no dispatches happened, I set the average to 0. In line 91, I calculate the success percentage, which for now is 100% if there was the least one dispatch. In line 94 to 96, I determine an overall rating based on the success percentage, average distance, and pending emergencies. In line 98, I get all responders from the map to display the total count. In line 100 to 107, I print the entire statistics section, including total emergencies, resolved ones, responders, average response distance, success percentage, pending emergencies, and the final rating. In line 133, I retrieve all emergencies and store them in an array. In line 116 to 122, I filtered the list to only include unresolved emergencies. In line 125 to 134, I performed a selection sort on these emergencies so they are arranged from highest to urgency to lowest. In line 136 to 139, I print a table header. In line 140 to 143, if no unresolved emergency exists, I print a message and exit the method. And lastly, the 145 to 151. Otherwise, I loop through the top N emergencies and print their ID, urgency, type, and the location. Now let's move on to testing and debugging. We designed to help manage emergencies, assign responders, and monitor the overall situation. Today, we were going to walk through its core functionalities, demonstrating how each option works, and then we'll dive into debugging scenarios. Our first step is to register an emergency. We'll use option 1, add emergencies. Imagine a fire just broke out downtown. Here, I've selected 1, and the system prompts me for details. Type, location, description, and urgency. I've entered fire for the type, downtown for the location, a short description for fire, and an urgency of 9. The system confirms and added E007, fire, downtown, urgent 9, and rest is no. Notice rest no, that means no responder has been assigned yet. This confirms our emergency E007 or the number 7 is now in the system. Now let's see all the emergencies currently in our system, including the one we just added. For this, we use option 2 to view all emergencies. As you can see, we have the list of emergencies ordered by some internal priority or entry order. Our number 7, the fire in downtown, is there, along with 6 others. Each entry shows its ID, type, location, and urgency. And crucially, whether a responder has been assigned. This list is vital for getting a snapshot of all active situations. An emergency isn't resolved without a responder. Let's add one using option 3. I've entered number 1 as the responder ID, fire as a type, and residential zone as their starting location. The system confirms responder added. Responder number 1 fire residential zone is available. This responder is now ready for dispatch. To verify our new responder and see all available units, we select option 4 to view all responders. Here's our full list of responder units. We all can see the number 1 fire truck residential zone available, confirming our addition. We also have other police, fire truck, and ambulance unit, all currently available. This overview helps us identify the suitable units for dispatch. Now for the critical step, dispatching a responder to an emergency. We'll use the option 5 to dispatch. The system first shows us all pending emergencies. Again, I've chosen dispatch emergency ID number 1, which corresponds to E001, the fire downtown. The system then intelligently identifies the closest or most suitable responders. In this case, F01, the fire truck from the downtown, it calculates the distance, shows the route, and updates the responder's status to busy. In this simulation, it even shows the responders finishing the becoming available again. The single dispatch has resolved E001 and the system recorded a 0 kilometer distance since the fire truck was already in downtown. After some activity, it's good to get an overview. Here we see the total emergencies registered 7 and the total emergencies resolved is number 1. That our E001, it also shows the total responders, the 7. Average response distance is 0.0 kilometer and the successful response is 0%. The overall system rating needs work is a good indicator that we have more to do. This report helps us evaluate the system's performance. Our system uses a graph-based approach to calculate distance and routes. Option 7 to print the graph, visualize this work. This output shows our interconnected locations. For instance, residential zone is 3 kilometers for downtown and 7 kilometers from Riverside. This is crucial for dispatching the closest available responder and calculating travel times efficiently.
Moving to a common scenario where debugging might be unnecessary, a continuous operation will use option 8 simulate. The simulation starts by processing the highest priority emergency, which is ID is E004 and the urgency is 10. Fire at industrial zone, it dispatches F02. Fire truck records the dispatch and resolves the case. Then it moves to the next highest, E005, urgency is 9. Medical, and at the airport hub, dispatching A02, ambulance. The simulation continues automatically dispatching responders based on urgency and availability. But what if, during this continuous process, we notice a problem? Perhaps a responder was dispatched to a location they couldn't reach, or an emergency wasn't marked as resolved even after a dispatch. Let's imagine the system kept trying to dispatch a medical emergency to a fire truck because of a logic error in a matching responder type to emergency type. That would be a bug. To debug this, I would immediately look at the simulate function code, specifically the part that selects responders based on emergency type and availability. If the system was incorrectly matching, I would trace the variable that holds the responder's type and the emergency required type. Using print statement or a debugger, I would check if best responder unit type is actually being compared correctly to emergency type. A common mistake could be a typo or a mismatch in how these types are stored. This ensures the right responder always goes to the right type of emergency.
So we've seen the SERMS console in action, from adding emergencies and responders to dispatching them, generating reports, viewing the network graph, and even running a full simulation. We also walk through a hypothetical debugging scenario, emphasizing the importance of robust logic in matching emergencies with appropriate responders. This system is designed to streamline emergencies response, and with careful testing and debugging, we can ensure it performs optimally when it matters most.